We begin our journey at a set of coordinates, a destination without a landmark, a location without a place. It is designated simply AT25P63. On any star chart, it is an unremarkable patch of night. Through the most powerful telescopes ever conceived by humankind, it remains stubbornly, profoundly, and perfectly dark. There are no shimmering nebulae here, no distant spiral galaxies. There isn't even the faint glimmer of a solitary wandering star. It is a window into a perfect velvet blackness, an abyss so complete it feels less like a part of our universe and more like a hole gouged out of the fabric of reality itself. For most of human history, we looked up and saw a cosmos filled to the brim, a celestial sphere crowded with gods, heroes, and mythical creatures. The night sky was a familiar populated ceiling. The idea of emptiness, of a true void, was a philosophical absurdity. Nature, the ancients argued, abhors a vacuum. How could there be nothing? Nothingness was not a state of being, it was the absence of it. This perception of a full universe was not just a myth, it was a deeply intuitive conclusion, one that our finest minds would reinforce for centuries to come. When Galileo first turned his rudimentary telescope towards the heavens, the universe did not become emptier. It became impossibly fuller. That hazy, milky band across the sky resolved into a river of stars, a torrent of countless individual points of light, more than anyone had ever dared to imagine. Every new advancement in optics seemed to confirm this initial finding. The cosmos was a treasure chest, and we had only just found the key. With each new look, we uncovered more jewels. William Herschel, with his colossal instruments, painstakingly mapped the sky, revealing a staggering density of stellar bodies. He believed our galaxy, the Milky Way, constituted the entirety of creation. A magnificent disc-shaped city of suns, and we, somewhere within it. Beyond its edges, perhaps nothing, but inside it was a metropolis of light. For a time, this was the prevailing view, a universe that was busy, dynamic, and compact. But there were anomalies. Faint fuzzy patches of light the astronomers called nebulae. Some saw them as nascent solar systems, swirling clouds of gas condensing to form new stars and planets within our own galaxy. They were proof of a universe in constant creation, a cosmic nursery further populating our already crowded home. Others, however, championed a more radical, almost unthinkable idea. They proposed these were not clouds at all, but entire galaxies in their own right. Island universes, the philosopher Immanuel Kant had called them. Vast stellar congregations like our own Milky Way, but separated from us by distances so immense as to be incomprehensible. The debate raged for decades, a foundational argument about the true scale of existence. If these nebulae were close, the universe was large and full. If they were distant, the cosmos was something else entirely. It was a paradigm shift waiting to happen, a truth hiding in the faint redshift of light from a spiral nebula in the constellation of Andromeda. The moment of revelation fell to an astronomer named Edwin Hubble, working in the crystalline air atop Mount Wilson in the 1920s. Using the colossal Hooker telescope, he found a specific type of star, a Cepheid variable, within the Andromeda Nebula. These stars are cosmic lighthouses. Their pulsation rate is directly linked to their true brightness. By comparing that intrinsic luminosity to how dim it appeared from Earth, Hubble could calculate its distance with unprecedented accuracy. The number he arrived at was staggering: 1,000,000 light-years. Andromeda was not a nearby cloud. It was a sister galaxy, a continent of stars utterly separate from our own. In that single observation, the known universe exploded in size. It was like a man who believed his house was the whole world suddenly discovering the existence of cities, countries, and continents. But this discovery was just the first tremor of a much larger earthquake. Hubble didn't stop there. He measured the distances to dozens of these galaxies, and in their light he found something deeply strange. The light from nearly every single one of them was stretched, shifted towards the red end of the spectrum. This was the Doppler effect, the same phenomenon that lowers the pitch of a siren as it speeds away from you. These galaxies were moving away from us, and the farther away they were, the faster they were receding. This was the ultimate demolition of the old static, crowded cosmos. The universe was not a static room filled with furniture. It was expanding, flying apart in all directions at once. To visualize this, imagine we are baking a loaf of raisin bread. The dough is the fabric of space-time, and the raisins are the galaxies. Let us place these raisins carefully throughout the unbaked lump of dough. Now, we put it in the oven. As the dough bakes, it expands, and it expands everywhere at once. From the perspective of any single raisin inside that loaf, all the other raisins would appear to be moving away from it. A nearby raisin would seem to move away slowly. A raisin on the far side of the loaf would be carried away by the expanding dough at a much greater speed. There is no center to this expansion. It is happening everywhere. Every raisin has the same experience. This is our universe. It is not that galaxies are flying through space like bullets. It is space itself, the very medium of existence, that is stretching, carrying the galaxies along for the ride. This expansion is the first and most profound reason for the emptiness. It has been taking the initial dense concentration of matter and energy from the Big Bang and stretching it out over an ever-increasing volume for 13.8 billion years. The result is a universe of almost unbelievable scarcity. The average density of the cosmos is about 5 hydrogen atoms per cubic meter. To put that into perspective, the best, most perfect vacuum chambers we can create on Earth still contain trillions of atoms in that same amount of space. Intergalactic space is emptier than anything humanity has ever experienced. It is an almost perfect nothing. Let us construct another image to grasp this void. Picture a cathedral. Not just any cathedral, but one whose vaulted ceilings stretch up into the stratosphere, whose stone floors extend across an entire continent. It is a structure of impossible scale and grandeur. Now, place a single grain of sand on the altar at its very center. That single grain of sand is the Milky Way galaxy. The vast, echoing, silent and lightless volume of the cathedral around it, that is the emptiness of intergalactic space. The scale is so extreme that our minds, evolved to navigate the crowded savannas of Earth, can barely begin to process it. We live inside that grain of sand, looking out into the incomprehensible cathedral, and we wonder why it seems so vacant. But even this image is not entirely accurate. The universe is not uniformly empty. Gravity, the great sculptor, has been at work since the beginning. Over billions of years it has gathered the sparse dust and gas of the cosmos into magnificent structures. Imagine threads of shimmering silk woven into a three-dimensional cosmic web. These filaments are where the galaxies are. They are the great highways of the universe, chains of galactic clusters stretching for hundreds of millions of light years. Where these filaments intersect, we find the great superclusters, the bustling metropolises of the cosmos, teeming with thousands of galaxies. But between these shimmering threads of creation lie the voids, vast, dark, and astonishingly empty regions of space. These are the cosmic badlands, spherical gulfs of near total nothingness, some of them hundreds of millions of light years in diameter. Our point of origin, the coordinates AT25P63, lies in the heart of one such place. A location like the Boötes Void, a region so empty that if our Milky Way were at its centre, we would not have known other galaxies existed until the 1960s. The night sky there would be an almost unbroken blackness. The emptiness we perceive is not just a matter of average density. It's a fundamental feature of the universe's architecture, a grand design of filaments and voids, of something and almost nothing. So how did this strange web-like structure come to be? What primordial architect designed a cosmos of such extreme contrasts? The answer takes us back to the very first moment of time, to a state of unimaginable temperature and density, the singularity of the Big Bang. The standard model of the Big Bang was a triumph of 20th century science, but it had deep, persistent problems. One was the flatness problem. The universe appears to have a perfectly flat geometry, which is a highly unstable and improbable state, like balancing a pencil on its point for 14 billion years. Another was the horizon problem. Regions of the universe on opposite sides of the sky are at the same temperature, yet they are too far apart to have ever been in contact or exchanged heat. It was as if two people who had never met, spoken, or communicated somehow wore the exact same outfit to a party. It suggested a connection in the past that our current understanding could not explain. In the early 1980s, a physicist named Alan Guth proposed a breathtaking solution, a modification to the very beginning of the story. He called it cosmic inflation. The theory suggests that in the first sliver of a second after the Big Bang, for a period lasting less than a trillionth of a second, the universe underwent a period of hyper-exponential expansion. It doubled in size, then doubled again and again, at least 100 times over, growing from smaller than a proton to larger than a grapefruit in an instant. This was not a gentle unfolding. It was the most violent event in cosmic history. The very fabric of space-time was stretched taut with unimaginable force. Imagine a microscopic canvas, painted with intricate, chaotic details at a quantum level. The paint is a turbulent foam of energy, with tiny random fluctuations in its density. Now, in an instant, grab the edges of this canvas and stretch it. Stretch it until it is billions of light years across. What happens to the painting? The immense violent stretching smooths out all the wrinkles and creases, solving the flatness problem. It makes the entire canvas uniform. It also explains the temperature uniformity. The entire observable universe was once a tiny, connected subatomic patch in thermal equilibrium. Inflation blew it up to cosmic scales so quickly that the different regions had no time to change, preserving that initial temperature signature. The horizon problem was solved. But what about those tiny quantum fluctuations in the paint? They too were stretched. Microscopic variations in density were magnified to astronomical proportions. The slightly denser regions became the seeds of gravitational collapse. They became the locations where matter would later congregate. They became the shimmering filaments of the cosmic web. The slightly less dense regions were stretched into the vast, empty chasms between them. They became the great voids. Inflation was the architect. It took the quantum randomness of the infant universe and etched it onto the heavens, creating the grand structure we see today. The terrifying implication here is that the emptiness is a foundational feature of reality. The universe looks empty because it was violently sanitized, smoothed out, and made vast before it was even a second old. The voids are not accidental gaps, they are a direct magnified image of the quantum uncertainty that existed at the beginning of time. This primordial act of creation set the stage, but another, more mysterious force is now directing the play, and its role is to deepen the emptiness, to ensure that the void will ultimately win. For most of the 20th century, cosmologists assumed the expansion of the universe must be slowing down. Gravity, after all, is the universe's great unifying force. Every galaxy, every star, every particle is pulling on every other. Like a ball thrown into the air, the cosmic expansion should be decelerating, pulled back by the collective gravity of everything within it. The only question was whether it would slow to a halt and fall back in on itself in a big crunch, or if it had enough momentum to coast forever, slowing but never stopping. In 1998, two separate teams of astronomers set out to measure this deceleration rate. They used distant supernova, exploding stars of a very specific type, as standard candles to measure cosmic distances with incredible precision. They pointed their telescopes, gathered their data, and ran the calculations. The results were not just wrong, they were impossible. The expansion wasn't slowing down at all, it was accelerating. Something was pushing the universe apart, overwhelming the collective pull of gravity. It was as if the ball thrown into the air suddenly ignited its own rocket engine and shot upwards, faster and faster. This was a discovery that shook the foundations of physics. Scientists gave a name to this mysterious influence: dark energy. We do not know what it is. It appears to be a property of space itself, an intrinsic repulsive energy of the vacuum. As the universe expands, more space is created, and with that new space comes more of this dark energy. Its effect, therefore, becomes stronger and stronger over time. The implications of this discovery are profound and deeply unsettling. Dark energy is the guardian of the emptiness. ensuring its eternal reign. It is actively pushing galaxies away from us at an ever-increasing rate. This creates a cosmic horizon, a point of no return. Galaxies that cross this horizon are receding from us faster than the speed of light. Not because they are travelling through space that fast, but because the space between us and them is being created so rapidly that even light cannot overcome the expansion. Their light will never reach us again. They will wink out of our sky, one by one, forever. Consider our cosmic future from this perspective. Imagine you are standing on a small island in a vast, dark ocean. All around you, you can see other islands, each with its own twinkling lights. But a strange, powerful current has begun to flow, originating from everywhere at once. It pushes all the islands away from you, and from each other. At first, the closest islands just seem to drift slowly, but the farther islands are carried away more quickly. Soon, the most distant islands begin to slip over the horizon. Their lights flicker and then vanish completely. As millennia pass, the process continues. More and more islands disappear until only your immediate neighbours, your own little archipelago, remain visible. Eventually, even they will be torn away by the relentless current. The ocean will grow until your island is the only thing you can see. You are utterly alone in a black, featureless expanse, with no evidence that any other land ever existed. This is the ultimate fate of our universe, the Big Freeze, or heat death. Astronomers in the far distant future, 1 trillion years from now, will look out into the night sky and see nothing but the stars of our own galaxy, which will have by then merged with Andromeda and our local neighbours. Beyond that, there will be absolute, perfect blackness. All other galaxies will have been pushed beyond the cosmic horizon, their light lost to us forever. All the evidence for the Big Bang, for the expansion of the universe, all the clues we use to piece together our cosmic history, will be gone. Future civilizations will exist in a state of profound cosmic ignorance, believing their lonely mega-galaxy is the entirety of creation. The terrifying truth is that the emptiness is not a static backdrop. It is an active, conquering force. Dark energy is ensuring that the universe becomes more empty with every passing second, and it is systematically erasing the history of its own creation. We, it turns out, live in a brief, privileged moment of cosmic clarity, and the window is closing. This leads us to the final, and perhaps most chilling reason for the apparent emptiness. It is not just a void of matter and energy, but seemingly a void of life and intelligence. The silence. Our galaxy alone contains up to 400 billion stars. We now know that planets are not the exception, but the rule. There are likely trillions of planets in the Milky Way. Even if we are conservative, a significant fraction of those should be rocky worlds in the habitable zone of their star, where liquid water could exist. The raw ingredients for life as we know it, carbon, oxygen, nitrogen, are abundant, forged in the hearts of stars and scattered across the cosmos. The universe has had billions of years for life to emerge and evolve. So, as the physicist Enrico Fermi famously asked his colleagues over lunch one day, "Where is everybody? If the universe is so vast and so old, it should be teeming with life, and at least some of that life should have evolved into technological civilizations. Some of those should have developed interstellar travel or communication. The galaxy should be noisy. It should be full of radio signals, probes, artifacts, and the engineered signatures of alien empires. Yet when we point our radio telescopes to the sky, back towards places like AT25P63, we hear nothing. Only the faint cold hiss of the cosmic microwave background radiation, the afterglow of the Big Bang. The silence is deafening. This contradiction between the high probability of extraterrestrial life and the utter lack of evidence for it is the Fermi paradox. There are many proposed solutions, but one of the most sobering is the concept of the Great Filter. The theory posits that on the long evolutionary path from simple chemistry to a galaxy-spanning civilization, there exists some barrier, some filter, that is extraordinarily difficult or impossible to overcome. There is a step in the process that is so improbable that almost no one makes it through. The terrifying question is, Where is this filter located in our own history? One possibility is that the filter is behind us. Perhaps the initial leap from non-life to life, abiogenesis, is the filter. Maybe the emergence of a self-replicating molecule is a 1 in a trillion fluke that happened only once, here on Earth. Or perhaps the filter was the leap from simple prokaryotic cells to complex eukaryotic cells, an event that took nearly 2 billion years to occur on our planet. Maybe intelligence itself is the barrier. In this scenario, we are the first. We are unique. The universe is empty because we are the only ones here. This is a lonely and monumental thought. It places an immense burden of responsibility upon us. If we are the only spark of consciousness in this vast darkness, then we are the universe's only way of knowing itself. And if we extinguish that spark, the cosmos may fall silent forever. But there is another, far more frightening possibility. The Great Filter might not be in our past. It could be in our future. Perhaps the path of technological advancement inevitably leads to a point of self-destruction. Perhaps every intelligent species that reaches our level of development discovers nuclear power and wipes itself out, or creates an uncontrollable artificial intelligence, or exhausts its planet's resources and collapses, or unleashes a genetically engineered plague. Perhaps there is some law of physics we do not yet understand, some catastrophic event that is triggered by advanced technology that sterilizes any civilization that reaches a certain threshold. In this horrifying scenario, the universe is not empty, it is a graveyard. The silence we hear is the silence of tombs. The great voids are cosmic cemeteries, filled with the ghosts of civilizations that reached for the stars and failed. The emptiness is not a blank slate, it is a warning. The barrenness of a place like a T25P63 is not the absence of potential, it is the evidence of a universal recurring tragedy. It tells us that the cosmos looks empty because it is the nature of intelligence to burn brightly, but briefly, before extinguishing itself forever. This is the most terrifying thought of all, that the silence is not an answer, but a prophecy. We stand on the shores of a cosmic ocean, on our pale blue dot. We look out towards the silent, empty coordinates of AT25P63, and we see the confluence of all these terrifying truths. We see an emptiness carved out by the unimaginable violence of inflation, an emptiness that is being relentlessly deepened and expanded by the mysterious push of dark energy, and an emptiness filled with a silence that may be the final testament to a great filter, a universal barrier that stands between us and a future among the stars. The universe is not empty by chance, it is empty by design, a consequence of the fundamental laws that govern it, and perhaps a consequence of the nature of intelligence itself. The void is not passive, is not. It is the result of powerful active forces, and yet we are here. Against all of these overwhelming odds in this vast, indifferent and dangerous cosmos, a small tribe of primates on a speck of dust has woken up. We have looked out into the great darkness, and have not just seen emptiness, we have begun to understand it. The terror of the void is matched only by the sublime miracle of our own consciousness. We are the universe's fleeting opportunity to witness its own grandeur and its own desolation. The emptiness is terrifying, yes, but our ability to perceive it, to question it, and to be awed by it is the most precious and improbable thing in all of existence. We are a brief, warm thought in a cold, eternal mind, and that perhaps is enough. And for every question we have ever asked of the cosmos, it has answered with a silence so profound it seems to stretch beyond time itself. We have built our civilizations under a canopy of predictable things, a celestial tapestry woven with the steady light of familiar stars and the gentle looping waltz of our planetary neighbours. There is a profound comfort in this cosmic clockwork, a sense that we inhabit a corner of the universe governed by understandable, immutable laws. We learn to chart the sky to predict the return of comets with the precision of a master watchmaker, and in doing so, we began to believe we understood the grand design. We convinced ourselves that the universe, for all its terrifying vastness, was fundamentally orderly, that the great cosmic ocean was one of tidal flows and gentle currents, not rogue waves. This belief became the bedrock of our cosmic perspective, a fragile shield against the infinite, humbling dark. We looked out and saw a masterpiece of gravitational architecture, a cathedral of light and motion where every star was a candle in its proper place, every galaxy a distant, shimmering rose window. And for a time, this beautiful illusion held. We mapped the spiral arms of our own Milky Way, a sprawling city of 100 billion suns, each on its own majestic multi-million-year journey around a supermassive black hole that serves as our galaxy's silent gravitational anchor. We learned to read the light from these stars, deciphering their chemical compositions, their ages, their very life stories from photons that had travelled for millennia just to end their journey in our instruments. This light told us stories of creation of stellar nurseries, where clouds of incandescent gas larger than our entire solar system collapse under their own weight to ignite the nuclear forges of new suns. These are the crucibles of existence, the very places where the carbon in your body, the iron in your blood, was first hammered into being inside a dying star's heart. We saw too the end of these stories. We witnessed stellar ghosts, the ethereal expanding shells of planetary nebulae, the last beautiful sigh of a sun like our own. We saw the true titans, the blue giants, live their short, furious lives and then detonate in supernovae, explosions of such unimaginable violence they can briefly outshine their entire host galaxy, seeding the cosmos with the heavy elements necessary for life, for planets, for us. We traced the intricate dance of galaxies themselves, great islands of stars bound together in clusters, slowly, inexorably pulling on one another across millions of light years. We saw them pirouette and merge in graceful, slow-motion collisions, their structures distorted by gravitational tides, their gas clouds shocked into furious new waves of star formation. This was the universe we came to know, a place of breathtaking scale and sublime patient processes. Its timescale was not our own. It dealt in eons, in epochs. The dangers it posed, like the eventual death of our own sun or the collision of our Milky Way with Andromeda, were so far in the future as to be abstract philosophical concerns. They were footnotes in the grand cosmic story, not immediate headlines. We built our observatories on the highest, driest mountains, turning our mechanical eyes toward the heavens, not with fear, but with a confident academic curiosity. We were cataloguing a known wilderness, mapping a territory whose fundamental rules we thought we had already deciphered. The darkness between the stars was just that emptiness, a quiet, passive void separating the great celestial engines. We stood on our small blue world, convinced that we were safe in our sun's gentle harbour, shielded from the true chaos of the interstellar deep. But the universe does not care for our comfort. It is not a manicured garden. It is a wild, untamed frontier, and it has travellers who obey no familiar map. Beyond the orbit of Neptune lies the Kuiper Belt, a scattered junkyard of icy bodies, the frozen remnants of our solar system's formation. And further out, still enveloping our entire system in a vast, ghostly sphere a light year across, is the Oort cloud. This is the realm of the long-period comets, trillion-strong swarms of ice and rock, orbiting our sun in such lazy, distant paths that a single journey can take 30 million years. They are the solar system's deep freeze attic, preserving the primordial chemistry of our birth. Most will never trouble us. They will continue their silent, solitary pilgrimage through the dark for eternity. But the galaxy is not a quiet neighbourhood. A passing star, a gravitational nudge from the Milky Way itself, is all it takes to disturb this delicate peace. A single piece of this ancient ice can be dislodged from its precarious orbit and sent on a new, fatal trajectory, falling inward toward the distant, beckoning light of our sun. For years we have watched them come. We see them first as faint, indistinct smudges in our telescopes. As they fall closer, the sun's warmth begins to work on them, sublimating their ancient ice into gas, creating the beautiful ghostly coma and the magnificent tail that can stretch for millions of miles across the sky. They are visitors from the edge of our own kingdom, messengers from our own deep past. We have learned their habits, their patterns, We track them, we name them, we calculate their orbits with exquisite precision. We can predict their closest approach to the Earth centuries in advance. They are a part of our system's family, albeit the strange reclusive cousins who only visit once every few thousand years. They are known quantities. Even the asteroids that lurk closer in the belt between Mars and Jupiter have become familiar. We have mapped hundreds of thousands of them, building a vast digital census of our local cosmic debris field. We've established a planetary defense network, a global chain of observatories standing as silent sentinels, their primary mission to scan the darkness night after night for any object on a trajectory that might intersect our own. This is a monumental undertaking, a testament to our species' ingenuity and our instinct for survival. Telescopes like Pan-STARRS in Hawaii and the Catalina Sky Survey in Arizona sweep vast swathes of the sky, taking thousands of images every single night. These are not the beautiful long-exposure portraits you see in magazines. They are rapid-fire snapshots of the cosmos, a relentless search for anything that moves. The sheer volume of data is staggering, far too much for any human to analyze alone. Sophisticated algorithms are the first line of defense computer programs designed to compare new images with older ones, looking for the telltale sign of a wanderer, a single point of light that has shifted its position against the fixed backdrop of distant stars. These algorithms are our bloodhounds, sniffing through terabytes of digital information for the faintest scent of motion. They flag thousands of potential candidates every night, most of which are known asteroids on their regular catalogued paths. But every so often the machine flags something it doesn't recognize, a ghost in the data, an anomaly. That is when the humans step in. Astronomers across the globe receive the alerts, their professional curiosity piqued. They pivot their own instruments, some in different hemispheres, to get another look, to confirm the sighting, to gather more data points. It is a global, collaborative, and often anonymous dance of discovery. One observatory makes the initial detection, another provides the crucial follow-up observations hours later that allow for a preliminary orbit to be calculated. The Minor Planet Center, the world's clearinghouse for all such data, becomes a hive of activity, collecting these scattered observations and fitting them together like pieces of a celestial puzzle. This system has worked for decades. It has found comets from the edge of our solar system, and it has identified asteroids that have passed harmlessly but uncomfortably close to Earth. It has reinforced our sense of security, our belief that we have built a shield of knowledge, a digital watchtower from which we can see trouble coming long before it arrives. We had come to trust the math, to believe in the elegant power of orbital mechanics to foretell the future. We thought we had accounted for all the variables. We were watching the front door diligently and tirelessly. We never imagined that something might come crashing through the wall. The first hint that our understanding was about to be shattered arrived as nothing more than a whisper, a few anomalous pixels on a digital sensor at the Atlas Observatory in Hawaii. The Asteroid Terrestrial Impact Last Alert System. Its very name speaks to its purpose, a final warning. On a clear, cold night, its software flagged a faint object, impossibly dim, moving with a speed and direction that felt subtly, inexplicably wrong. It was given a provisional bureaucratic designation, a string of letters and numbers that belied its significance. To the astronomers who first saw the alert, it was just another candidate, another piece of rock or ice to be catalogued. The initial excitement was purely academic. Was it a new comet, a peculiar asteroid from the far reaches of our system? The first few data points were fed into the computers and a preliminary orbit was plotted. The result was intriguing but not yet alarming. It appeared to be a long-period comet, perhaps one that had been nudged out of the Oort cloud thousands of years ago, now making its first fiery passage around our sun. The astronomical community buzzed with quiet anticipation. A new visitor offered a new opportunity for science, a chance to study pristine material from the dawn of our solar system. But as more observatories around the world trained their gaze on this faint spectre, a new, deeply unsettling picture began to emerge. Each new data point, each new position measurement, made the initial orbit less and less stable. The numbers refused to resolve, the puzzle pieces didn't fit. Astronomers working late into the night felt a growing sense of unease. The elegant elliptical path they expected to see was warping, stretching into something else, something alien, They reran the calculations, checked their software for bugs, even questioned the integrity of their own telescopes. The math, however, was ruthless. It kept giving them the same impossible answer. This object was not in a closed loop around our sun. It wasn't one of ours. The line of its trajectory was open a shape known as a hyperbola. It was a cosmic one-way ticket. This visitor had come from the void, from the fathomless, terrifying space between the stars. It was falling through our solar system, and once it passed, it would continue on its journey never to return. It was a true alien, the first of its kind to be detected with such clarity. The designation changed. The letter C for comet was replaced with an I for interstellar. 3I, Atlas, the third interstellar object ever confirmed. The excitement in the scientific community was electric, a once-in-a-generation discovery that promised to rewrite textbooks. Here was a messenger from another star system, a physical sample of a place we can only dream of visiting. What secrets did it hold? What story was written in its alien ice? The world's largest telescopes, including the Hubble and the new James Webb, were being retasked, their schedules cleared to focus on this singular, extraordinary guest. The initial orbital data, while shocking, was also reassuring in its own way. It showed 3I, Atlas, on a trajectory that would take it through the outer solar system over the course of several years. It would make its closest approach to the Sun well beyond the orbit of Jupiter. It was a fascinating scientific curiosity, but it posed no threat. It was a distant spectacle, a chance to study an interstellar traveler from a safe and comfortable remove. Humanity had years to prepare, years to study it, years to unlock its secrets as it slowly coasted through our celestial neighborhood. Then came the second tremor, a scientific aftershock that was far more terrifying than the initial discovery. It began with a small team of astrophysicists at a European observatory. They weren't satisfied with the public orbital solution. Something about the object's brightness, the way it was reflecting sunlight, didn't quite line up with its calculated distance. It seemed just a little too bright, a little too distinct for something so far away. They started from scratch, gathering every single observation from every observatory they could access, building their own independent model of the object's path. They worked for 72 hours straight, fueled by coffee and a gnawing suspicion that the rest of the world had missed something vital. Their computers churned through the complex gravitational equations, factoring in not just the Sun but the subtle pulls of Jupiter and Saturn, even the minuscule but persistent pressure of solar radiation on the object's surface. And as the final refined trajectory appeared on their screens, the quiet hum of the server room was replaced by a stunned, horrified silence. The official models were wrong. Not just slightly wrong, but catastrophically, fundamentally flawed. A subtle but critical error in the initial data processing, a miscalculation in the way the first few observations were weighted, had skewed every subsequent prediction. It was an honest mistake, the kind of small error that can cascade through a complex system with devastating consequences. The new corrected orbit was not a gentle sweeping curve through the outer planets. It was a dagger aimed directly at the heart of the inner solar system. And the timeline, the comfortable multi-year window that had allowed for such calm academic study, was a fiction. The object wasn't coasting. It was screaming toward us with a velocity that had been dangerously underestimated. It wasn't years away from its closest approach. It was months. The visitor from the stars was no longer a distant curiosity. It was an imminent arrival. The timeline had changed. And with that one chilling realization, the greatest scientific discovery of the century instantly became a frantic, desperate race against a clock we never knew was ticking. Humanity's placid gaze into the cosmos was over-replaced by the startling, terrifying knowledge that something unknown and unpredictable was coming, and it was coming far sooner than anyone thought possible. What if the most important message in human history was not a signal but a delivery? What if it wasn't beamed from a distant star as a whisper of radio waves, but was instead hurled across the interstellar void, a physical object on a collision course with our understanding? For millennia, our ancestors looked to the heavens and saw permanence, a divine clockwork of breathtaking regularity. The stars were fixed points in a grand celestial map, their movements charted by priests and prophets who saw in their cycles the unchanging will of the gods. The planets, the wanderers, followed intricate but ultimately knowable paths. This was our universe, a majestic, predictable, and fundamentally closed system. And into this perfect order, from time to time, something terrible and beautiful would arrive. A comet. To the ancient mind, it was not an object of ice and rock. It was a premonition, a celestial omen painted across the night with a brush of ethereal light. It was a sword in the sky, a tear in the divine fabric, a harbinger of plague, war, or the death of kings. These apparitions obeyed no known rules. They appeared without warning, blazed with an otherworldly fury, and vanished back into the abyss, leaving behind only fear and folklore. They were messages from a realm beyond our own, their meaning debated in hushed tones in palaces and temples across the globe. For thousands of years, this was our relationship with the unexpected visitors to our skies, one of terror, of reverence, but never of understanding. We saw the effect, the luminous ghost in our heavens, but the cause remained shrouded in divine mystery, a cosmic phenomenon that underscored our own fragility in a universe we could observe but not comprehend. That profound and terrifying ignorance began to dissolve in the flickering candlelight of the 17th century. A revolution in thought, spearheaded by minds like Isaac Newton, proposed a universe governed not by divine whim but by universal mathematical laws. Gravity, the same force that pulls an apple to the earth, was revealed to be the invisible architect of the cosmos, the master puppeteer pulling the strings of planets, moons, and even those ghostly celestial visitors. It was Newton's contemporary Edmund Halley who applied this radical new understanding to the historical sightings of the great comets. Sifting through ancient records, he noticed a pattern, a recurring visitor appearing roughly every 76 years. He made a prediction of breathtaking audacity that the comet of 1682 was the same one seen in 1530 and 1607, and that it would return again in 1758. Halley did not live to see his prophecy fulfilled, but when that point of light appeared exactly where and when he said it would, humanity's relationship with the cosmos was forever altered. The comet now bearing his name was no longer a divine omen. It was a physical object, a citizen of our own solar system, bound by the same gravitational laws as the Earth beneath our feet. It was a dirty snowball trapped in a vast elliptical embrace with our Sunday. Its appearance was not a warning but a confirmation, a testament to the power of human reason to decode the universe's hidden language. We had for the first time tamed a ghost. This triumph ushered in a new era of cosmic cartography. We began to map our local neighborhood with astonishing precision, realizing our solar system was far more crowded and far more dynamic than we had ever imagined. We discovered the great belt of rubble between Mars and Jupiter, a graveyard of planetary dreams filled with millions of asteroids, the rocky remnants of our system's chaotic birth. These were the close neighbors, the potential threats, their orbits weaving a complex web through the inner solar system, but our explorations pushed further into the cold, dark frontiers. Beyond the orbit of Neptune, we found the Kuiper Belt, a vast icy disk populated by frozen worlds like Pluto and countless smaller bodies. This was the source of the short-period comets, those visitors like Halley's, that return on timescales of a few decades or centuries. They are flakes of primordial ice, occasionally nudged by the gravity of the giant planets into orbits that bring them careening toward the sun, where they blossom into the spectacles we see from Earth. And even beyond that, in the truly profound depths of interplanetary space, we theorized the existence of the Oort cloud. It is less a place and more of a concept, a vast spherical shell of perhaps 1 trillion icy bodies enveloping our entire solar system, extending almost a light year into the darkness. This is the realm of the long-period comets, those that take thousands or even millions of years to complete a single journey. They are the deep sleepers disturbed only by the faint gravitational tug of a passing star or the tidal forces of the galaxy itself. Once awakened, they begin a slow, multi-millennial fall toward the distant pinprick of our sun, their journey a silent testament to the sheer scale of our star's gravitational domain. For 2 centuries, this was the accepted map. Our solar system was a vast, sprawling but ultimately self-contained kingdom, an empire of gravity ruled by one star. Everything we saw, every planet, moon, asteroid and comet was born here. They were family, however distant or estranged. The Oort cloud formed an immense conceptual wall around our home, the boundary beyond which lay only the unimaginable emptiness between the stars. The idea that an object could cross that void, that it could journey from one solar system to another, was the stuff of pure speculation, a theoretical possibility so remote, so statistically improbable, that it remained firmly in the realm of science fiction. The universe, we believed, did not make deliveries from star to star. The space between suns was an inviolate empty ocean. To protect ourselves from the known dangers within our own cosmic backyard, we built new eyes. Not the brass and glass tubes of old, but silent robotic sentinels. Automated telescopes networked across the globe, programmed to scan the entire visible sky every few nights. Among the most advanced of these is Atlas, the Asteroid Terrestrial Impact Last Alert System. Its mission is brutally pragmatic to find the rocks that could kill us. Perched on volcanic peaks in Hawaii, Chile, and South Africa, its wide-field cameras drink in the night sky, capturing vast mosaics of the heavens. Night after night, the system takes pictures, and powerful software subtracts the new images from the old, searching for one thing: a point of light that has moved. Every single night, this digital sentinel flags thousands of such movers. The vast majority are known asteroids, their orbits already logged in our celestial ledgers. But a few are new. The system automatically calculates a preliminary orbit for these discoveries, attempting to determine if they are a familiar inner-system asteroid, a more distant Kuiper Belt object, or a long-period comet falling in from the cold abyss of the Oort cloud. It is a tireless, impersonal process, an automated search for the next Halley, or more urgently, the next Chicxulub, the asteroid that ended the reign of the dinosaurs. For years, the system performed its duty flawlessly, cataloguing the denizens of our home system, refining our map and standing guard. It saw only what it was programmed to see, what we expected to see, members of our own solar family. Then, on October 19th, 2017, the machine flagged an anomaly, a faint, fast-moving streak of light that simply did not compute. When astronomers traced its path backward, they were stunned. The orbit wasn't a closed loop, an ellipse tethered to our sunday. It was a hyperbola, a trajectory that was wide open. This object wasn't falling in from our Oort cloud. It was screaming through our solar system from a direction that made no sense, moving far too fast to be gravitationally bound to our star. It was a tourist, an emissary from the interstellar deep. We called it Oumuamua, a Hawaiian name meaning a messenger from afar arriving first. It was a discovery that shattered a century of astronomical certainty. The inviolate ocean between the stars was not empty, it was navigable. Oumuamua was a cosmic enigma, unlike anything we had ever seen. It was small, dark, and tumbling, end over end. Most bizarrely, as it whipped around the sun and headed back out into the void, it gently accelerated, pushed by some unseen force. It had no visible tail, no cometary outgassing to explain this push. Was it a new type of object? A nitrogen iceberg breaking apart? Was it impossibly thin? A natural solar sail? Or was it something else? The questions were intoxicating and unsettling. For the first time, we had touched something that was not ours. A piece of another world, another sun's family had grazed our home, and then vanished as quickly as it came, leaving behind a profound paradigm shift. We were not alone, not in the way we had always meant. Our solar system was not an island, but a port of call on a galactic ocean teeming with unseen traffic. Oumuamua could have been a freak occurrence, a once-in-a-civilization event. But then, less than 2 years later, it happened again. In August 2019, an amateur astronomer named Gennady Borisov spotted a new comet. As observatories around the world turned to track it, the same astonishing truth emerged. Its trajectory was also a hyperbola. This was another traveller from beyond. We named it 2I, Borisov, the second confirmed interstellar object. Unlike the mysterious Oumuamua, Borisov was reassuringly familiar. It looked and behaved exactly like the comets from our own Oort cloud, sporting a magnificent tail of dust and gas as it was warmed by the sunday. It was a stunning confirmation. Oumuamua wasn't a fluke. The galaxy was indeed seeding space with these celestial nomads. We had now seen 2 of them in 2 years. Suddenly, the question was no longer times. If times they existed, but how many were out there? How many had we missed? The discovery of these first two interstellar visitors recalibrated our expectations. It was like living your entire life in an isolated valley, believing it to be the entire world, only to discover a highway cresting the nearest ridge with traffic from lands you never knew existed. The robotic sky surveys, including Atlas, had their software updated. The algorithms were taught to look for the telltale signature of a hyperbolic orbit, to flag not just the local threats, but the cosmic tourists. Astronomers now knew what to look for. The hunt was on for the third visitor for 3I. We were watching the sky with new eyes, aware that any point of light could be a message from another star. The anticipation in the astronomical community was palpable. What would the next one be like? Another bizarre mystery like Oumuamua, or another familiar comet like Borisov? When would it arrive? The answer, it turned out, had already arrived. It had been logged, catalogued, and filed away without fanfare. On the night of January 7th, 2023, the Atlas system in South Africa did its job. It took a picture. The software compared it to a reference image and found a new, infinitesimally faint smudge of light in the constellation of Aquila. The automated system performed a routine calculation. The orbit appeared to be a long, lazy parabola, consistent with a brand new first-time visitor from the deepest, coldest reaches of our own Oort cloud. It was given a provisional bureaucratic designation C, 2023, a 3. The C stood for comet. The 2023 A3 meant it was the third such object discovered in the first week of January of that year. To the system, and to the handful of astronomers who glanced at the initial data, it was just another data point, an unremarkable frozen pebble beginning its multi-million-year fall towards a distant sun it had never before met. It was ours. It was predictable. It was a completely routine discovery, one of dozens made every year, destined for a footnote in an astronomical circular. There was no alert, no sudden flurry of emails, no sense of cosmic revelation. It was just another ghost from our own attic, its future path across our sky, seemingly written in the unchanging ink of gravity. Nothing about its faint, distant signature suggested it was anything other than what it appeared to be. Nothing hinted that its origins were unimaginably more profound, its trajectory impossibly wrong, or that its arrival would force us to question not just our place in space, but our place in time. That faint smudge of light was not a predictable member of our solar family. It was an imposter. And in its quiet, unassuming detection, a cosmic fuse had been lit, a countdown that was proceeding far faster than anyone could possibly imagine. And so, with the world's great observatories now synchronized, their colossal eyes all turned toward that single, onrushing point of light, the great scientific campaign began. The initial thrill of discovery, that electric moment of first contact, settled into a disciplined global hum of activity. From the arid heights of the Atacama Desert to the volcanic peak of Mauna Kea, data began to pour in. Not a trickle, but a deluge, a torrent of numbers representing photons captured after a journey of billions of miles, each one a tiny messenger from the interstellar darkness. We thought we knew the language these messengers spoke. It is the universal language of physics, of light and gravity, a cosmic lingua franca we have spent centuries learning to translate. The first task was simple, almost rote, to chart its heartbeat. This is what astronomers call a light curve, a measure of an object's brightness over time. For a simple asteroid, this rhythm is as predictable as a metronome, a gentle sine wave rising and falling as its oblong body tumbles through space, presenting a larger, then a smaller face to our telescopes. A comet's light curve is a bit more complex, a steady rhythm overlaid with the rising crescendo of its coma brightening as it nears the sunday, predictable, understandable, governed by the clean laws of rotation and reflection. But the heartbeat of 3I, Atlas, was wrong. From the very first extended observations, the data felt off. The gentle rhythmic rise and fall we expected was there, but it was haunted by a strange arrhythmia. There were sudden, inexplicable flares moments, where the object would momentarily double in brightness, like a cosmic flashbulb firing off in the void. These weren't the grand, sustained outbursts of a fragmenting comet nucleus. They were sharp, almost instantaneous, lasting for mere minutes, before fading back to the baseline. And just as unnerving were the dips, sudden troughs in the light curve that were too deep, too abrupt to be explained by simple rotation. It was as if something were momentarily casting a shadow over it, or as if the object itself were briefly impossibly dimming. Initially, these anomalies were dismissed as noise. Atmospheric interference, a glitch in a sensor, cosmic rays striking a CCD, these things happen. You learn to filter them out to find the true signal hidden within the static, but the static refused to go away. A team in Chile would report a flare at 0300 Universal Time. An hour later, as the Earth turned, a team in Hawaii would report that the baseline brightness was now 5% lower than it should have been. Then an automated observatory in Australia would catch a sudden deep fade. When the plots were overlaid, a disturbing picture emerged. This wasn't random noise. It was a pattern, but a pattern we couldn't read. The object was pulsing, sputtering like a faulty celestial engine. The steady, predictable rhythm of a tumbling rock was absent. In its place was a chaotic, syncopated beat, a message written in a language of light and shadow that we had never encountered before. The global astronomical community, connected by high-speed networks, became a single planetary brain trying to solve this puzzle. Theories flew back and forth across encrypted channels. Could it be a binary object, two pieces orbiting each other so closely that they periodically eclipse one another? The math was run, the models were built, but they failed. A binary system would produce a regular, predictable pattern of dips. This was erratic, unscheduled. Could its shape be incredibly complex, like some cosmic shard of glass, with dozens of reflective facets catching the sunlight at odd angles? Possible, but the sheer intensity of the flares seemed to demand more than just a lucky reflection. It was as if the object itself was generating these flashes, not merely reflecting them. As the teams grappled with the confounding light curve, a second, more profound anomaly began to surface, one that shook the very foundations of our predictions. It came not from the photometers measuring brightness, but from the astrometrists, the meticulous celestial cartographers who measure position. Their job is to take the object's picture night after night, measuring its location against the fixed backdrop of distant stars with astonishing precision. From these positions you can build an orbit. You can trace its path back into the interstellar void from which it came, and you can project its path forward into our own solar system. This is the heart of celestial mechanics, a science so precise we can predict eclipses to the second centuries from now. It is the domain of gravity, the undisputed king of the cosmos. We had plotted the orbit of 3I, Atlas. We knew where it was going, but it was starting to drift off course. The deviation was minuscule, a few hundred kilometers over a journey of tens of millions. It was the equivalent of a rifle bullet fired from a mile away, missing its target by the width of a human hair. To you or me, a stunning success of prediction. To an astronomer, a catastrophic failure. In the unforgiving mathematics of the cosmos, a miss is a miss, and this tiny persistent error was screaming that something was fundamentally wrong with our assumptions. The object was moving faster than it should have been. It was accelerating ever so slightly, as if a ghostly, invisible hand were giving it a gentle, constant push forward. Now, comets do this. It's a known phenomenon. As a comet nears the sun, its icy surface heats up and turns directly into gas, a process called sublimation. This outgassing acts like a tiny natural rocket engine, venting jets of gas and dust into space. If these jets happen to fire in the right direction, they can indeed alter the comet's trajectory, creating what are known as non-gravitational forces. We have models for this. We see it all the time. The behavior is well understood. You plug the numbers in, and the model corrects the orbit, matching the observations perfectly. So the teams plugged in the numbers for 3I, Atlas. They modeled the outgassing based on its size and distance from the sunday, and the models broke. The acceleration wasn't right. It was too smooth, too consistent for the chaotic, sputtering jets of a typical comet. A comet's outgassing is messy. It happens in fits and starts, as different pockets of ice are exposed to sunlight and erupt. This should produce a correspondingly noisy acceleration, a path that jitters and wanders slightly. But the acceleration of 3I, Atlas, was different. It was a clean, steady, persistent thrust. Furthermore, the amount of thrust required to explain its deviation was far greater than what our models predicted. For it to be accelerating this much from simple cometary outgassing, it would need to be venting a truly colossal amount of material. It should have been a brilliant spectacle, one of the brightest comets ever seen, with a vast shimmering coma and a tail stretching across the sky. But it wasn't. It was still just a faint, unassuming point of light. The engine was running, but we couldn't see the exhaust. This was more than just a puzzle. It was a paradox, a deep, irreconcilable conflict between two different sets of data. The astrometrists measuring its position said it was accelerating like a powerful comet. The photometrists measuring its brightness said it looked like a nearly inert asteroid. Both sets of data were impeccable. Both were confirmed by independent teams using different instruments on opposite sides of the world. Both could not be true, and yet they were. This is the moment when scientific apprehension begins to curdle into genuine dread. It's the moment when you realize the phenomenon you are studying is not just a new example of a known class of object, it's something else entirely. The very ground of celestial mechanics, a bedrock of certainty for 300 years, felt like it was shifting beneath our feet. The debate intensified. Could our understanding of gravity itself be incomplete at these interstellar velocities? It was a fringe, almost heretical idea, but it was whispered on late-night calls. Could the sun be exerting some other force, some pressure from its magnetic field or solar wind that we had failed to properly model? The numbers were crunched. Simulations covering every known aspect of heliophysics were run on supercomputers. Nothing worked. Nothing could account for that stealthy, powerful push. Desperate for a tiebreaker, for a clue that could resolve the paradox, all attention turned to the third and most powerful tool in the astronomer's arsenal, the spectroscope. If photometry tells you how bright something is and astrometry tells you where it is, spectroscopy tells you what it times is asterisk. By splitting the faint light from 3I, Atlas, into its constituent colors, its rainbow spectrum, we could search for chemical fingerprints, the dark absorption lines, or bright emission lines that betray the presence of specific atoms, molecules. This would be the final arbiter. The spectrum would reveal the composition of the material being vented into space. It would tell us once and for all if this was a comet of water, ice, and dust, or something far stranger. The largest telescopes on Earth were tasked with this monumental challenge. Capturing enough photons from such a dim, distant object to generate a detailed spectrum requires hours of exposure time, with the telescope tracking its target perfectly as the Earth spins beneath it. The first results that trickled back were baffling. They were, in a word, clean. Too clean. We expected to see the strong, unambiguous signature of hydroxyl, the OH molecule, which is a breakdown product of water vapor in sunlight. It is the defining fingerprint of a water-ice comet. It was there, but it was incredibly faint, nowhere near strong enough to account for the object's tremendous acceleration. The primary fuel for a cometary engine, water, seemed to be almost absent. Then, what was pushing it? As the teams integrated their data, stacking observation upon observation to pull the faintest signals out of the noise, other stranger fingerprints began to emerge from the darkness. There were faint emission lines that didn't correspond to the usual suspects, like carbon monoxide or carbon dioxide. Some teams identified signatures tentatively associated with molecular nitrogen, a substance that only sublimates at incredibly low temperatures, suggesting the object was colder and more primitive than anything we had ever seen from our own Oort cloud. Another group, pushing their equipment to the absolute limit, claimed to have detected the spectral trace of argon, a noble gas. An inert gas that shouldn't be bound to a celestial body at all unless it was trapped under immense pressure deep inside. This was the final devastating blow to the standard cometary model. The object's engine wasn't running on simple water ice. It was powered by something else, something exotic, and the outgassing wasn't a gentle, sun-driven sublimation from the surface. The presence of those deep freeze volatiles, combined with the erratic flares in the light curve, pointed to a different process. It suggested that the activity was geological, that the outgassing was coming from deep within the object, venting through fissures or cryovolcanic plumes. The flares were not reflections, they were eruptions. The dips were not shadows. They were moments when a plume of dense, dark dust briefly obscured the nucleus. The steady acceleration wasn't from a surface turning to gas, but from a deep-seated, continuously active thermal engine. We were not looking at a passive melting snowball, we were looking at an active world, a tiny frozen and yet geologically dynamic body hurtling toward us from the interstellar deep. This was the confrontation, not between rival teams of astronomers, but between humanity's accumulated knowledge and one single object that refused to obey our laws. Every piece of data that came in deepened the mystery. Its light was a chaotic pulse. Its path was an impossible curve. Its chemistry was alien. The neat boxes we used to label the heavens, comet, asteroid, planetesimal were shattering. 3I, Atlas, didn't fit in any of them. It was its own category. A chilling realization began to dawn in control rooms and university offices around the globe. We had made a fundamental error right at the beginning. We had assumed that this visitor, because it came from the stars, would still play by the familiar rules of our own solar system. But it didn't. It brought its own rules, and as it continued, its inexorable acceleration drawing ever closer, a terrifying new question began to form. A question that eclipsed all the technical debates about its composition and trajectory. If our models of its physics were this wrong, if we had failed so completely to understand its fundamental nature, then what did that say about our most important prediction of all? The one that told us not just what it was, but where it was, going, and when it would arrive. And so, we watched. For months, humanity's gaze had been fixed on that single ghost-white point of light, a traveller from a star we will never know. 3I, Atlas was a guest in our home, a sublime silent wanderer whose path we had meticulously charted. We had traced its majestic sweeping arc through the outer solar system, a trajectory calculated and recalculated by the world's finest minds. The consensus was a masterpiece of celestial mechanics, a prediction of beautiful clockwork precision. It would be a distant spectacle, a once-in-a-civilization event observed from a safe and comfortable remove of tens of millions of miles. Our models were elegant, our confidence absolute, but the universe in its infinite and often terrifying subtlety does not care for human confidence. It cares only for the truth, a truth that was beginning to whisper from the deepest chasms of our data, a dissonant note in an otherwise perfect cosmic symphony. The first whispers came not as a shout, but as a flicker on a screen in the silent, chilled dome of the very large telescope in Chile. There, Doctor. Aris Thorne, a man whose life was a conversation with numbers, found himself locked in a quiet battle with a ghost. For weeks, the orbital plot for 3I, Atlas, had been haunting him. Every new observation, every fresh data point from the worldwide network of observatories should have snapped perfectly onto the line of prediction, reinforcing the elegant curve of its calculated journey. Instead, they were off. The deviation was infinitesimal, a mere handful of pixels on his monitor, a statistical ghost so small that most had dismissed it as instrumental noise or the faint gravitational chatter of the asteroid belt. But Thorne saw a pattern. The error wasn't random, it wasn't chaotic noise. It was consistent, it was directional. With every passing day, 3I, Atlas, was pulling ever so slightly ahead of its predicted position, as if it were impatient, eager to keep an appointment we knew nothing about. It was a discrepancy that bordered on the absurd, a rounding error with a strange and persistent intelligence. To even suggest the official trajectory was wrong, the trajectory confirmed by dozens of institutions, was professional heresy. The mathematics were sound, the physics unimpeachable. The great gravitational wells of Jupiter and the Sun had been accounted for down to the millionth decimal place. Every conceivable influence had been modelled and factored in, and yet the ghost remained. Thorne found himself returning to the raw telemetry night after night, long after his colleagues had departed the observatory silent, save for the hum of cooling fans and the distant Chilean wind. He was chasing a phantom, a feeling that the very foundation of their understanding was built upon a single flawed assumption. What he wrestled had they missed? What fundamental truth about this silent visitor had they failed to see? The problem he began to suspect was not with the math of its motion, but with the assumptions about its substance. Every calculation of its path depended on one critical variable, its mass. To know its mass, you needed to know its size and its density. But But you can't simply place an object hundreds of millions of miles away on a cosmic scale. You have to infer its properties. The primary method was to measure its brightness, its albedo, how much sunlight it reflected back at our telescopes. From the start, 3I, Atlas, had been unusually bright, suggesting it was either very large or covered in highly reflective material, perhaps pristine water ice, from the cold, dark spaces between the stars. The consensus leaned towards the latter, a standard model for an interstellar comet. This gave them a mass, a gravitational fingerprint, that dictated how it should dance with our sun. All of our elegant predictions, all of our assurances of a safe and distant flyby, rested on the simple belief that we knew what this thing was made of. This was the pillar Thorne decided to attack. Poring over the spectrographic analysis, the chemical breakdown of the light reflecting off its surface, he found the supporting evidence thin. The initial readings were noisy, ambiguous. Yes, there were traces of water ice, but there were also confusing signatures of silicates and complex carbon compounds, all jumbled together in a way that defied easy categorization. It was a chemical chimera. What if he posed in a late-night email to a trusted colleague, "We were wrong about its reflectivity"? What if 3I, Atlas, wasn't a brilliant white snowball, but something much darker, something less reflective? If it were darker, then to be as bright as it appeared in our sky, it would have to be substantially larger, a lot larger, and if it were larger, even with a low density, its mass would be significantly greater than the official figures. It would be a heavyweight masquerading as a featherweight. The idea was met with polite skepticism. The models were robust, the peer review had been thorough, but Thorne's relentless persistence began to open hairline fractures in the certainty. He argued that the object's brightness could be deceptive. Perhaps it was experiencing brief intermittent bursts of outgassing sporadic plumes of dust and vapor that were temporarily shrouding it in a reflective cloud, tricking our telescopes into seeing a brighter, smaller object than what was actually there. These fleeting shrouds would average out over time, creating the illusion of a consistently high albedo. They weren't seeing the true face of 3I, Atlas. They were seeing its veil. This was his heresy, that the foundational measurement upon which everything else was built could be a profound misinterpretation. He was suggesting that the anchor point for all their calculations was not set in stone, but was instead drifting in a fog of incorrect assumptions. The key to unlocking the truth, he realized, lay not in its brightness, but in that other nagging anomaly, its speed. The tiny, persistent acceleration that everyone had dismissed as noise. In the standard cometary model, outgassing is a chaotic process. As a comet nears the sun, ice sublimates into gas, erupting from fissures and vents in random directions. These jets push the comet around unpredictably like a sputtering, badly made firework. It's a messy, stochastic process that introduces jitter into an orbit, not a clean, consistent push in a single direction. But the acceleration Thorne was tracking was anything but random. It was smooth. It was constant. 3I. Atlas was moving as if it possessed its own engine, a ghostly, imperceptible thruster, gently but relentlessly pushing it forward along its line of travel. This was the moment of epiphany, the kind of terrifying ice water in the veins clarity that scientists both crave and dread. It struck Thorne not in front of a monitor, but on a drive down the mountain from the observatory, the star-dusted Chilean sky sprawling above him. The two anomalies weren't separate problems. They were two sides of the same coin. The outgassing wasn't random at all. It was focused. For some reason, due to its spin, its shape, or the unique properties of its alien crust, the gas and dust were not erupting chaotically. They were being channeled, perhaps, from a single dominant region on its surface that by sheer cosmic chance was aligned perfectly to act as a natural low-thrust engine. It was a celestial blowtorch firing continuously, invisibly pushing the object onward faster and faster. He raced back to his terminal, his mind ablaze. The implications were staggering. This wasn't just a scientific curiosity. This was a fundamental rewriting of the entire encounter. He began building a new model from scratch, a model born of a heretical thought. First, he threw out the old mass estimate, treating it as an unknown variable. Then he introduced a new force into the equations of motion, a tiny but continuous non-gravitational acceleration, a phantom thrust aimed directly along the object's path. He didn't know its precise strength, so he started running thousands of simulations, programming the computer to iterate through every possible value for the mass and the thrust, searching for a combination that would make the persistent orbital error, the ghost in the machine, vanish completely. He was asking the computer a simple question: what must 3i Atlas be for it to move in the exact way we observe? For 2 days, the supercomputers at the European Southern Observatory churned running the numbers, sifting through a universe of possibilities. Thorne barely slept, existing on stale coffee and adrenaline, watching as the program relentlessly sought a solution. Most of the simulations crashed, returning mathematical nonsense. But then, in the deep silence of the third night, the program converged. It found a perfect match, a single unique combination of mass and thrust that made every single data point from the last several months of observation snap perfectly onto a new, terrifyingly different trajectory. The ghost was gone, the error was zero, but the answer it provided was a nightmare. To achieve its observed acceleration with such a subtle thrust, the model showed that 3i Atlas had to be monstrous. Its mass was not just slightly larger than predicted, it was nearly 75 times greater. It wasn't a glittering snowball a few kilometers across. It was a dark, hulking behemoth, a mountain of primal rock and exotic ices stretching perhaps 30 kilometers from end to end, a true leviathan from the interstellar deep. Its surface was not bright and reflective, but dark as coal, absorbing the sun's energy and using it to power its focused directional outgassing with terrifying efficiency. It was a stealth object of immense scale, and its steady, relentless thrust had been acting upon its enormous mass for years, subtly but irrevocably altering its course as it sailed through the lonely void toward us. With trembling hands, Thorne commanded the system to plot the new trajectory based on this horrifyingly plausible new model. The elegant, distant curve that had reassured the world dissolved, replaced by a line that was sharper, more aggressive, a blade cutting directly into the heart of the inner solar system. The screen refreshed, drawing the new orbital path in a stark, blood-red line. It was no longer a gentle sweep past the orbit of Mars. This new path hooked inwards, dramatically tightened by the object's immense mass and its ceaseless, ghostly acceleration. It showed 3i Atlas crossing Earth's orbit, not in 18 months but in 7, and the predicted closest approach, the flyby distance that had been a comforting 60 million miles, had collapsed. The new number that solidified on the screen made the air go thin in Thorne's lungs. The simulation predicted a closest approach of less than 400,000 miles. It was going to pass within the orbit of the moon. Disbelief warred with the cold, hard certainty of the mathematics. This couldn't be right. It was a mistake, a flaw in his code, a hardware glitch. He ran the simulation again and again. The result was always the same, an unblinking digital oracle delivering the same catastrophic prophecy. He immediately sent his findings, his code, and his raw data in a single heavily encrypted package to a small, trusted circle of colleagues at NASA's Jet Propulsion Laboratory and the Minor Planet Center. The subject line of the email contained only 3 words: urgent, verify. Now, he knew that what he was about to do would shatter the calm, ignite a firestorm, and forever change humanity's relationship with the stars. He was about to sound an alarm that could never be unsounded. The response was an instantaneous electric shockwave through the global astronomical community. In California, Dr. Kenji Tanaka's team at JPL dropped everything. They fed Thorne's data into their own independent systems, some of the most powerful orbital dynamic simulators on the planet. They worked for 36 hours straight, fueled by a growing sense of dread, as their own models one by one confirmed the unthinkable. Thorne was right. The ghost in the data was real. The outgassing was a focused engine. The mass was immense. The old timeline was a fantasy. Their own screens soon glowed with the same horrifying red line, the same impossibly close encounter, the same terrifyingly short countdown. Within 2 days, a dozen other institutions around the world had secretly verified the results. The consensus did not fracture. It was pulverized. The truth was now inescapable, an incontrovertible, mathematically proven reality. The carefully managed scientific narrative of 3i Atlas, the story of a benign and wondrous visitor, had been a fiction. We had not been observing a celestial tourist. We had been tracking a cosmic bullet, and we had miscalculated its speed and its aim with devastating consequences. The time for quiet observation and academic curiosity was over-vaporized in an instant. The global scientific scramble had begun a frantic, desperate race against a clock that we now knew was ticking far, far faster than we had ever imagined. The guest who had come for dinner was not merely passing through the foyer, it was now understood to be on a collision course with the dining room table, and we were all seated around it, suddenly aware of the profound silence that had just fallen. Our timeline had not just shifted, it had been shattered, and a new, terrifyingly urgent one had just begun. The silence that followed was not one of peace. It was the heavy, breathless vacuum that comes after a thunderclap, the stunned quiet in the moments before the world catches fire. Across dozens of institutions on screens displaying the final, verified orbital solution for 3I, Atlas the numbers glowed with an apocryphal light. The elegant, sweeping arc we had all grown comfortable with, the one that gave us years to prepare, was gone. In its place was a slash, a brutal, precipitous line aimed almost directly into the heart of the inner solar system. The timeline hadn't just changed, it had been shattered. A quiet academic curiosity had, in the space of a single keystroke, become a global emergency. What followed was a cascade of controlled panic, a symphony of frantic coordination played out across encrypted channels and hastily arranged video calls that spanned every time zone. The first casualty of this new reality was scientific decorum. Long-planned observational campaigns, some representing the culmination of entire careers, were suddenly on the chopping block. You cannot simply ask the director of the European Southern Observatory to pivot the Very Large Telescope on a moment's notice. You cannot tell a team that has waited 5 years for their 30-hour window on the James Webb Space Telescope that their investigation into the atmospheres of nascent protoplanets must be sacrificed for something that yesterday was a mere curiosity. Yet these were the calls being made, not as requests but as non-negotiable necessities. The arguments were fierce. They were bitter. To the astronomers who had dedicated their lives to mapping the cosmic microwave background or charting the movements of dark matter 3I, Atlas was an interloper, a celestial vandal crashing the most exclusive party in the universe. But the cold, hard physics of the situation was an unassailable argument. Every single model, from the most conservative to the most speculative, now painted the same terrifying picture. Our window of opportunity for observation was not measured in years but in months. The object's approach vector meant that for a precious fleeting period it would pass almost perpendicular to Earth's orbital plane, offering our most powerful instruments an unprecedented view of its northern pole as it blazed towards the sun. This was a once-in-a-civilization opportunity, and to miss it was unthinkable. One by one, the glass and steel leviathans of our world turned their gaze. In the high, arid desert of the Atacama, the 4 colossal units of the VLT, each with a mirror over 8 meters wide, began the slow, delicate process of slewing towards a new set of coordinates in the constellation of Hercules. Schedules were wiped clean. Data pipelines were reconfigured. The new priority consumed everything. Farther north, the twin eyes of the Keck Observatory in Hawaii, perched above the clouds on Mauna Kea, abandoned their survey of distant galaxies. Their new target was a single, faint point of light, a phantom that had suddenly become the most important object in the sky. But the true jewel, the one that sparked the most heated debate, was the James Webb Space Telescope. This magnificent golden-eyed observatory parked a million miles from Earth was our single greatest asset. Its infrared sensitivity was precisely what we needed to pierce the dusty coma that was likely beginning to form around 3I Atlas, to analyze the chemical composition of its outgassing, and perhaps even to measure its surface temperature. The director of the Space Telescope Science Institute faced an unenviable choice: disrupt a meticulously planned multi-year schedule of peer-reviewed science, or risk humanity's only chance to get a clean, detailed look at the visitor before it grew too active and chaotic. The decision, when it came, felt like a judgment. Dozens of projects were indefinitely postponed. The Webb would be retasked. We were committing our most advanced instrument, our great celestial eye, to stare down the barrel of this incoming cosmic rifle. Simultaneously, a different kind of observation campaign was spinning up. It wasn't enough to just see this thing. We needed to listen. The vast, synchronized arrays of radio telescopes, the Very Large Array in New Mexico, ALMA in Chile, the Green Bank Telescope in West Virginia, began a coordinated effort to detect any form of emission. The initial goal was purely scientific, to search for hydroxyl masers, a telltale sign of water ice sublimating in the vacuum of space, which could give us our first real clue about its composition. But beneath that official objective lay a deeper unspoken question, a sliver of apprehension that no one dared voice in official meetings. We were pointing the most sensitive radio receivers ever built at an object displaying anomalous acceleration, a ghost from another star system. We were listening just in case it had something to say. The sheer logistical challenge was a nightmare. Coordinating these disparate assets, many operated by different nations with their own priorities and protocols, was like trying to conduct a global orchestra where every musician is playing a different tune in a different language. Data had to be standardized. Observation windows had to be deconflicted. A new ad hoc global network of astronomers, engineers, and data scientists was born out of pure necessity, working around the clock, fueled by caffeine and a growing sense of dread. This was no longer a marathon. It was an all-out sprint, and we were already leagues behind the starting pistol. Inside this crucible of urgency, the scientific consensus began to fracture. The initial data on 3I, Atlas's non-gravitational acceleration, the strange persistent thrust that was propelling it forward, had been a curiosity. Now it was the central terrifying mystery. The leading theory, the one everyone clung to for comfort, was cometary outgassing. As the object approached, the sun ices on its surface would sublimate, turning directly into gas and creating jets that acted like small natural rocket engines. It was a well-understood phenomenon seen in countless comets from our own Oort cloud. It was the safe, rational explanation, but the numbers didn't feel quite right. The acceleration wasn't sporadic or chaotic as you might expect from unpredictable jets firing off a tumbling, irregular body. It was smooth, it was constant. As more tracking data poured in from the newly mobilized observatories, the trajectory models became more and more refined, and the problem only deepened. The thrust vector was too stable. It was as if the object had a designated forward and was applying a gentle, continuous push from its rear. A schism formed in the community. On one side were the traditionalists who argued that we were simply witnessing a unique but ultimately natural cometary behavior. Perhaps 3I, Atlas, was a pancake-shaped object spinning in such a way that its outgassing was focused in a single direction. Perhaps its composition was dominated by a substance like molecular nitrogen, which would sublimate gently and evenly far from the sun. They built complex models to prove it, twisting physics to fit the uncomfortable observations. Their argument was an appeal to cosmic mediocrity. The universe is vast, and we were bound to encounter strange things. There was no need for exotic explanations. On the other side, a smaller, quieter group of scientists began to explore the fringes. They were the astrophysicists and planetary scientists who looked at the clean, persistent acceleration curve and felt a cold knot of intellectual discomfort. They pointed out that the object was still incredibly far from the sun, much farther than where water ice, the primary driver of cometary activity, typically begins to sublevate with such force. The numbers, they argued, suggested an efficiency of thrust that was difficult to reconcile with the chaotic, messy process of natural outgassing. They didn't use the word artificial, not yet. To do so was career suicide, but they started publishing theoretical papers with titles like On the Potential for High Tensile Strength Materials in Interstellar Objects, an Analysis of Isotropic Acceleration in Non-Gravitational Trajectories. It was a code, a way of asking the unspeakable question without actually saying the words. This debate was the engine driving the race to refine the orbital models. Every new data point was a weapon seized upon by one faction or the other to bolster their case. The exact point of closest approach, the perigee, became a moving target. At first, it was predicted to be well outside the orbit of Mars. Then, as the new acceleration data was factored in, the line crept inward. It crossed Mars's orbit. It began to approach the orbit of Earth. The error bars on the prediction were still enormous, spanning millions of kilometers, but the direction of revision was terrifyingly consistent. With every new calculation, the threat grew more intimate. Our planet, once a distant spectator, was now uncomfortably close to the object's path. The pressure became so immense that in the most secure meetings at NASA and the European Space Agency, an even more radical idea began to be discussed. It was a measure of pure desperation, a Hail Mary pass on a planetary scale, a rapid response intercept mission. The logistics were beyond daunting. They were nearly impossible. We had nothing on the launch pad ready to go. The fastest probes we had ever designed took years, even a decade, to reach targets in our own outer solar system. 3I, Atlas, was moving at a speed that mocked our best chemical rockets. To catch it would require a launch vehicle that didn't exist, a trajectory that was almost a straight line and a timeline that was brutally short, yet they started drawing it up. Engineers were pulled from other projects to work on Project Nightwatch, a top-secret feasibility study. Could we repurpose an existing satellite bus? Could we strip a military-grade rocket of its normal payload and fit it with a simple camera and spectrometer, turning it into a kamikaze probe? Ideas like advanced solar sails or a radical gravitational assist around Venus were floated, each more improbable than the last. The plan was not to stop it or even deflect it. That was pure fantasy. The goal was simply to get a single fleeting close-up look, to get one definitive photograph, one clean spectral reading that would tell us exactly what was hurtling towards us. The fact that this plan was being seriously considered at all was a testament to how profoundly the situation had changed. We were no longer confident we knew what we were dealing with, and that ignorance was now an existential liability. And then, inevitably, the story broke. It was impossible to keep a secret this big, a secret that involved thousands of people and the realignment of the world's most visible scientific instruments. It started not with an official announcement, but with a leak, a blog post from a disgruntled graduate student whose thesis project had been indefinitely shelved. He posted the preliminary orbital plot, the one showing the blue line of Earth's orbit and the angry red slash of 3I Atlas's trajectory getting closer and closer. From there, the firestorm ignited. Within hours, it was the lead story on every news network on the planet. The carefully managed scientific debate spilled out into the chaotic public square, where nuance and caution were the first casualties. News tickers blinked with terrifying simplified headlines: mystery, object on accelerated path, scientists divided over interstellar threat timeline to impact shortens. Cable news channels convened panels of experts, some of whom had never studied orbital mechanics in their lives, to speculate wildly. Social media became a churning vortex of fear memes and outright disinformation. Conspiracy theories bloomed in the digital darkness, claiming it was a government hoax, or conversely, that governments were hiding the even more terrible truth. For those of us inside the scientific effort, this public awakening was a devastating blow. The intense pressure we already felt was now magnified 1,000-fold. Every calculation was scrutinized, every email potentially leaked. The weight of our work had changed. We were no longer just scientists trying to solve a fascinating cosmic puzzle. We were now the custodians of a global anxiety, the sole arbiters of a fact that could determine the future of our species. The growing public clamour was a constant humming distraction, a backdrop of noise that threatened to drown out the faint signals we were so desperately trying to hear from the void. The world was now watching our every move, and as the James Webb Space Telescope finished its delicate week-long reorientation and locked onto its new target, we knew the next phase was about to begin. The theoretical debates were over, the logistical scrambling was done. Soon, the first photons from this accelerated Enigma photons that had travelled for untold millennia through the interstellar darkness would finally arrive. They would fall upon a tiny golden mirror 1,000,000 miles from Earth, and they would begin to tell us their story. We had turned the collective eye of humanity towards the approaching spectre. We could do nothing now but wait for it to show us its face, and so the vigil ends. Not with a sudden alarm, but with a quiet, synchronized shift in posture across 100 control rooms. A collective intake of breath as the final countdown clocks, which for months have dominated giant screens, now simply read 0. The moment is upon us. The interstellar traveler, the cosmic riddle designated 3I, Atlas, has crossed an invisible threshold in space, a point of no return in our quest for knowledge. It is now closer to us than Mars has ever been, a fleeting neighbour in the grand, silent ballroom of the solar system. For the next 72 hours, it will blaze through the crosshairs of humanity's most powerful eyes, a singular focus for a planet holding its breath. The torrent of data we have craved, the deluge of answers we have gambled our resources and reputations on, is about to begin. Every radio dish, from the sprawling plains of New Mexico to the arid deserts of Chile, turns like a congregation to face the incoming truth. Every space-based observatory, a silent sentinel in the void, reorients its mirrors for the most important photoshoot in a generation. The faint, ghostly signal that we have tracked for years is about to become a roar. The whispers from deep space are about to become a symphony. The very first photons to resolve from pinpricks into pixels arrive not on Earth but 1,000,000 miles away at the second Lagrange point. There, the James Webb and Hubble space telescopes, orbiting in perfect gravitational balance, perform a delicate cosmic ballet. Freed from the blurring veil of our atmosphere, they drink in the pure, undiluted light of our visitor. The initial images flash onto screens at the Space Telescope Science Institute, and a stunned silence descends. What we had imagined as a comet, or perhaps a vaguely potato-shaped asteroid, is something far more alien, far more complex. The object is not a monolith, it is a shard, a jagged, violently fractured piece of something that was once much, much larger. It tumbles through space with a slow, wounded grace, an off-kilter rotation that speaks of a catastrophic past. Its surface is a bewildering mosaic of light and shadow. Vast regions are darker than coal, absorbing nearly all the sunlight that strikes them, suggesting carbon-rich primitive materials. But woven through this profound blackness are veins of something else entirely, glistening, crystalline structures that catch the sun's rays and scatter them back at us with an almost metallic bluish sheen. It looks less like a rock and more like a piece of cosmic geology, an exposed cross-section of a world we've never known. As Hubble captures the visible spectrum revealing this shocking topography, Webb pushes our vision beyond the limits of our eyes into the infrared. It sees not just the shape of 3I, Atlas, but its heat, and the thermal map that begins to form is a new chapter in the mystery. The dark regions are unexpectedly warm, absorbing solar energy and radiating it back slowly. But the crystalline veins, the shiny metallic-looking faults running across its surface, are intensely, unnervingly cold. It's a thermal inversion, a paradox that makes no immediate sense. In our solar system, dark things get hot and bright things reflect light, staying cooler. This object is breaking the rules, and then we see them. The source of its anomalous non-gravitational acceleration, the phantom force that has been pushing it, speeding up its arrival. From deep within the coldest, darkest fissures, Webb's infrared eyes detect faint, intermittent plumes of gas. They aren't the broad, dusty fans of a typical comet erupting from a sun-warmed surface. These are focused, collimated jets bursting out like laser beams from the interior of the object itself. They are almost invisible to the naked eye, a ghostly exhalation that is nevertheless powerful enough to act as a celestial engine, altering the traveler's path across the heavens. We are not watching a comet sublimate, we are watching something bleed. Now, the second wave of data arrives a different kind of light. This is the work of the great spectrographs on the ground, colossal instruments designed to perform a cosmic autopsy from 100 million miles away. They capture the faint light reflected from 3I, Atlas, and like a prism, shatter it into its constituent parts, a rainbow barcode of chemical composition. Each dark line in that spectrum is a fingerprint, the unique signature of an element or molecule absorbing its preferred wavelength of light. The first results are in a strange way disappointingly familiar. The broad signatures of silicates are there, the building blocks of rock. We see carbon-complex organic molecules locked in the dark material, confirming a primitive origin. It is at its most basic level a recognizable piece of the cosmos. But the science teams push the instruments to their absolute limits, staring at the spectrum for hours, accumulating photons, letting the signal build until the faintest, most subtle details begin to emerge from the noise. And that is when they find what should not be there. Deep in the infrared portion of the spectrum in the precise wavelengths, Webb is designed to see faint absorption lines appear that have no easy explanation. They are the spectral fingerprints of noble gases xenon, argon, krypton, not as free-floating atoms but trapped within a crystalline lattice of water ice. This is a clathrate hydrate, a structure that can only form under immense pressure and at incredibly low temperatures, conditions found in the deep, dark nurseries of protoplanetary disks far from any star. This isn't the fluffy, porous water ice of a common comet. This is ancient high-pressure ice, a fossil from the very birth of a solar system. It's a stunning discovery, a direct sample of the primordial ingredients that build worlds. Yet it only deepens the central paradox. These ices are hypervolatile. The slightest warmth should cause them to sublimate, to burst forth. If 3I, Atlas, were a simple snowball of these materials, it should have disintegrated long before it ever reached our sun. It should be a raging, brilliant comet, not a dark, fractured rock with ghostly internal jets. The object's very existence, its structural integrity, seems to defy the nature of the materials it's made from. The data is screaming two different stories, one of a dense, rocky body that can withstand the rigors of interstellar travel, and another of a fragile, icy relic that should have vanished eons ago. This is where the third stream of information becomes the decisive one. It comes not from light, but from radio waves. The newly upgraded Arecibo planetary radar in Puerto Rico and the Goldstone solar system radar in California begin their assault. They transmit fantastically powerful beams of radio energy, hundreds of kilowatts that cross the void in minutes, strike 3I, Atlas, and bounce back. The returning echo is infinitesimally faint, a whisper that must be painstakingly sifted from the cosmic static. But within that echo is a treasure trove of information. The Doppler shift in the returning frequency tells us with breathtaking precision the object's speed and rotation. By mapping the echoes across its surface, we can build a three-dimensional model resolving features down to the size of a football stadium. The initial radar maps confirm the visual data, the jagged angular shape, the strange tumbling motion. But radar does something light cannot. It penetrates the surface. While most of the signal bounces off the immediate exterior, a tiny fraction burrows deeper into the porous, fractured body, revealing clues about its internal structure. The radar teams notice something extraordinary. The echoes returning from the dark, carbonaceous regions are clean and sharp, indicating a dense, solid surface. But the echoes from the colder crystalline veins are messy, scattered, and slightly delayed. The radio waves are traveling through these regions, bouncing off multiple layers within, telling us that these are not surface features at all. They are deep, complex fracture zones, canyons that run into the heart of the object. And it is from the bottom of these canyons that the jets are erupting. The source of the thrust is not on the sunlit surface. It is deep inside, shielded from direct sunlight. The aha moment ripples through the global science community as all three datasets are laid on top of one another. The visual imagery, the infrared heat map, the chemical spectra, and now the subsurface radar scans. The pieces of the puzzle, which for so long seemed to belong to different boxes, suddenly snap into place with a resounding, paradigm-shifting click. A single, coherent, and utterly astonishing picture emerges. 3I, Atlas, is not a comet. It is not an asteroid. It is a survivor. A refugee from a cataclysm that destroyed its home world billions of years ago in a star system we will never know. The dark, dense material is not just carbon. The spectrographs recalibrating for this new model detect the unmistakable signature of heavy metals, iron, and nickel fused with silicates. This is material from the core mantle boundary of a differentiated planetary body. A world that was once large enough to have its heavy elements sink to the center, forming a metallic core surrounded by a rocky mantle. We are looking at a fragment from the collision that shattered that nascent planet. But that is only half the story. The deep crystalline fissures, the sources of the object's mysterious power, are the key. When this fragment was ripped from its parent body, the unimaginable violence of the impact created a network of deep cracks and faults throughout its structure. As this hot, glowing piece of shrapnel flew out into the cold darkness of its native interstellar space, it passed through the icy outer regions of its own destroyed solar system. There in the freezing void, the hypervolatile gases, the xenon, the argon, the primordial water didn't just coat the surface. They were driven deep inside, forced into the still warm cracks and fissures of the planetary fragment, where they flash froze under immense pressure into those exotic clathrate ices we detected. They became trapped, sealed away deep within a protective casket of rock and metal. For billions of years, 3I Atlas journeyed through the interstellar dark, a perfect time capsule, its volatile heart kept frozen and stable by the near absolute zero of deep space. It was a loaded gun waiting for a trigger, and our sun was that trigger. As it approached our solar system, the gentle, pervasive warmth of our star began to penetrate the object's rocky exterior. It was not enough to heat the surface significantly, but it was enough to slowly, conductively warm the interior. Deep within those fissures, the ancient high-pressure ices began to sublimate, turning directly into gas. The pressure built and built until it reached a breaking point, bursting forth in the focused, powerful jets that Webb saw and the radar confirmed. The traveler wasn't being pushed by the sun. It was firing its own internal primordial engines powered by the ghost of its long-dead solar system. The central conflict is resolved. The accelerated trajectory is no longer a mystery, but the logical, inevitable consequence of the object's unique and violent history. We have witnessed something entirely new, not a pristine leftover from our own system's formation, but a scarred, battle-hardened messenger from another. It is a testament to the sheer chaos and astonishing resilience of the cosmos. Every planetesimal, every asteroid, every world in our own solar system is a survivor of a similar age of violent construction. But here in 3I, Atlas, we have a direct glimpse into the alternative, not the story of success, but the anatomy of failure. The pieces of a world that could have been sent across the unimaginable gulf between the stars to deliver its story to our doorstep. We have found more than just a rock. We have found a memory written in the language of physics and chemistry. The timeline has not just changed. Our entire perspective on the architecture of solar systems, on the sheer variety of objects plying the interstellar void, has been irrevocably wonderfully expanded. We solved the puzzle of what 3I, Atlas, is only to be confronted by the far grander questions of the universe. It came from the secrets of its birth and the silent epic story of its impossibly long journey home to a sun that was never its own. And so the phantom recedes. 3I, Atlas, the ghost that haunted our skies, and our headlines now shrinks back into the profound silent black from which it came. Its searing tail, once a celestial blowtorch pointed at the heart of our world, is now just a dissipating wisp of memory, a trail of cosmic breadcrumbs leading back toward a star we will never know. The frantic, sleepless nights spent in observatories from Chile to Hawaii have given way to a strange and echoing quiet. The world which held its collective breath for so long has exhaled, but the air we breathe now is different. It is thinner, charged with a new and sobering awareness. The crisis has passed, but the revelation it delivered remains burned into our consciousness, like the afterimage of a blinding flash. We survived the close approach. We dodged the celestial bullet. What we are left with in the unnerving calm of the aftermath is the chilling knowledge of how little we truly knew and how fragile the timeline we inhabit always was. The story of 3I, Atlas, will be told for generations, not merely as an astronomical event, but as a defining moment in humanity's coming of age. It began, as these things so often do, as a whisper in the data, a faint smudge on a digital plate, barely distinguishable from the countless other distant wanderers. It was a curiosity catalogued and given a sterile designation, another ghost flitting through the graveyard of the outer solar system. We tracked it with a detached academic interest, its trajectory calculated on the reassuringly vast scales of millennia. But then came the anomaly, a flicker in its path, a subtle, almost imperceptible deviation that, when fed into the unforgiving logic of our computers, shattered our comfortable timeline to pieces. The date of its arrival, once a distant abstraction for future astronomers to ponder, suddenly collapsed, rushing toward us with terrifying speed. It was this moment, this violent recalculation, that transformed 3I, Atlas, from a scientific subject into a global protagonist, Suddenly, the world was galvanized by a singular purpose. We witnessed a mobilization of intellect and technology, unprecedented in human history, a frantic, desperate race against a clock that was not of our making. It was a race to understand. Rival nations shared top-secret observational data, proprietary algorithms were made open source overnight, and the world's greatest minds formed a sprawling virtual command center, connected by encrypted lines and a shared sense of profound urgency. We pointed every instrument we had at the approaching enigma. From the colossal mirrors of our greatest telescopes to the sensitive antennas of our deep space networks, every eye we possessed was turned outward, staring down the barrel of this cosmic shotgun. For a few terrifying weeks, humanity was united not by hope, but by a shared and palpable fear of the unknown. We watched, we measured, we debated, and we prepared for a future that was rewriting itself with every passing hour. The experience has left an indelible mark. It proved that in the face of an existential threat, we are capable of setting aside our terrestrial squabbles, but it also exposed the terrifying gaps in our armor, the vast empty patches in the net we have cast around our world. Now, in the wake of its passage, the real work begins. The terabytes of data, the precious photons captured during those harrowing days, have become our Rosetta Stone for the interstellar void. For decades, we looked out at the space between the stars and saw a near-perfect vacuum, a desolate, empty expanse separating lonely islands of light. Oumuamua was a strange anomaly, a fleeting glimpse of something that shouldn't have been there. Borisov was a confirmation that such things were possible but perhaps rare. 3I Atlas has torn that map of the cosmos to shreds. It was not just a messenger, it was a delegate from a vast, unseen population. Its composition, a bizarre amalgam of heavy metals and exotic ices we had previously only theorized could exist, told us a story of its origin system, a system perhaps racked by cataclysmic violence, a place where planets were shattered, their molten cores flash-frozen and flung out into the galactic tide. This object was a piece of shrapnel from a distant, ancient war between worlds, a war fought by gravity and chaos alone. Studying its spectral signature was like performing an autopsy on a creature from another biosphere. We found isotopes in ratios that defied the models of our own solar system's formation, suggesting its parent star was of a different generation born from a different cloud of primordial gas and dust. We saw how its surface had been weathered and scarred, not by the familiar energies of our own sun, but by the relentless bombardment of high-energy cosmic rays during its millions of years adrift in the dark. It was a relic, a time capsule carrying a chemical fingerprint from a place we can only dream of. Its arrival has fundamentally recontextualized our understanding of galactic ecology. The space between stars is not an empty desert. It is a dynamic, teeming wilderness, filled with the debris of creation and destruction. There are countless trillions of these silent travelers, ranging from city block-sized fragments to rogue worlds larger than Jupiter, all moving on their own inscrutable paths. They are the galaxy's dark matter, not in the cosmological sense, but in the most literal one matter that is there but which we cannot see. We are not living in an isolated bubble. We are living in a cosmic city full of unmarked, unlit speeding traffic, and we have just been reminded of how recklessly we have been crossing the street. This realization leads us to the most sobering lesson of all, the urgent, undeniable necessity of a true planetary defense system. For too long, the concept has been relegated to the pages of science fiction and the speculative budgets of space agencies. It was seen as a luxury, a problem for a distant, more advanced future. 3I Atlas has disabused us of this foolish, arrogant notion. Its unexpected timeline change was the universe's final warning. We were lucky this time. The object was large enough to be a global threat, but small enough that its trajectory could be nudged by non-gravitational forces, like outgassing the very forces that changed its timeline. But what happens when the next one is a solid 10-kilometer chunk of iron and rock, a dead, inert projectile, whose path is governed by nothing but the brute force of gravity? What happens when its trajectory is immutable, its destination locked on our world? What do we do when the timeline changes? and this time there is no room for a near miss. The conversations are now happening in earnest in the halls of power and the research labs that were so recently on the front lines. We can no longer afford to be passive observers cataloguing threats as they stumble into our field of view. We must become active guardians. This means building a new generation of sentinels of the void. We need space-based observatories with wider eyes and faster reflexes positioned far from Earth to provide us with what we lacked this time, the precious currency of advance warning. We need a network of dedicated survey telescopes whose sole purpose is to scan the darkness hunting for these faint, fast-moving interstellar shadows. But detection is only the first step. We must also develop and deploy a rapid response capability, a planetary immune system. This means investing in the technologies we have only ever simulated: high-energy laser arrays that can heat and vaporize the surface of an object to gently alter its course, fleets of hypervelocity kinetic impactors designed to deliver a precise surgical nudge, and sophisticated gravity, tractors that can patiently tug a threat onto a benign new path. Building these systems will be the great engineering challenge of the 21st century, a modern-day Apollo program with stakes that are infinitely higher. It will require international cooperation on a scale that makes our recent collaboration on 3I, Atlas, look like a dress rehearsal. It will mean treating planetary defense not as a scientific curiosity, but as a fundamental piece of global infrastructure, as essential to our long-term survival as clean water and a stable climate. We build seawalls to protect our cities from rising oceans, and we must now build a celestial shield to protect our entire world from the gathering cosmic tide. The alternative, a future spent gambling with extinction every time a new visitor appears in our skies, is simply unacceptable. Our complacency has been shattered, and in its place we must build a permanent, unwavering vigilance. 3I, Atlas, held a mirror up to our civilization, and in it we saw our own shocking vulnerability. Ignoring that reflection would be the ultimate act of self-destruction. Beyond the practicalities of survival, this encounter has irrevocably altered our place in the universe. We have been forced to confront a profound truth: our solar system is not a sanctuary. It is a temporary harbour on the shore of a vast and turbulent galactic ocean, and its waters are rising. We can no longer think of ourselves as isolated, the sole protagonists in our own cosmic play. We are part of a much larger interconnected ecosystem, subject to the migrations and whims of a population we are only just beginning to comprehend. Every star you see in the night sky is a potential origin point for the next visitor. Every one of them has likely ejected countless fragments of its own planetary system into the void, and some of them right now are hurtling through the darkness, on a course that will one day intersect our own. This knowledge changes everything. It imbues the night sky with a new sense of depth, a latent dynamism that is both terrifying and exhilarating. The stars are no longer just distant passive points of light, they are the lighthouses of other shores, and the space between them is full of unseen ships. This forces us to ask a new set of questions. If objects like 3I, Atlas, are so common, has Earth been visited before? Could some of the great extinction events in our planet's past, those mysterious die-offs not clearly linked to asteroid impacts from within our own system, have been caused by one of these interstellar interlopers? Are we in a very real sense the survivors of a long and intermittent cosmic bombardment? The evidence may lie buried deep within the geologic record, waiting for us to look again with new eyes. To search for those alien chemical fingerprints in ancient layers of rock and ice. The story of our own planet's history may be intimately tied to the stories of these travelers from afar. We are connected to the wider galaxy by invisible gravitational threads and the random chaotic arrival of its wandering children. We are not alone, not because we have found intelligent life, but because we have discovered that the very substance of other star systems is constantly raining down upon us, shaping our world and our destiny in ways we are only now beginning to grasp. So where do we go from here? The data from 3I, Atlas, will be analysed for decades, yielding new insights with every passing year. The political and scientific debates it has sparked will shape the future of space exploration and international policy. But the most significant change is the one that has occurred within us. You can feel it when you look up at the night sky. It no longer feels entirely safe. It no longer feels entirely empty. There is a sense of motion, a realization that we are passengers on a small, fragile vessel moving at incredible speed through a crowded and unpredictable environment. We have been given a glimpse behind the curtain of the cosmos, and what we saw there was not a quiet clockwork emptiness, but a dynamic, chaotic, and ultimately dangerous reality. It is a reality we must now learn to live with. Our story, the story of humanity, has always been defined by our response to the unknown. We are a species that looks at the horizon and feels the irresistible urge to see what lies beyond. For centuries, that horizon was an ocean or a mountain range. Today, it is the void itself. The arrival of 3I, Atlas, was not an ending. It was a violent, shocking beginning. It was the universe ringing a doorbell that we didn't even know we had, announcing the arrival of a guest we were not expecting. We have survived this visit. We have learned. We have been humbled. But we know with a certainty that chills us to the bone that there will be others, countless others. They are out there now, moving through the silent dark, their timelines still unwritten, their trajectories still unknown. They are coming. The question is no longer times. If time's another unexpected visitor will come and change our timeline. The only question that truly matters now is when it happens again, will we be ready undefined?